Guess for the first one.
Great, thank you so much, Adam. Okay. Yeah, I think this is going to be a really good follow-on from the last talk. I'm excited. So, hi everybody, my name is Gus Smith. I'm a PhD candidate, a fifth-year PhD at University of Washington's Pulse Lab. I'm studying under Zach, who I think he's in the room, or he just was. And today I'm going to be talking about why we should generate compilers from hardware models. Not necessarily a new idea, as we just saw from the past talk, but I'm going to be talking about why now is the time to do this. So first, let me shout out all my co-authors in Pulse, Ben, Vishal, Andrew, Renee, and Zach. I think some of them are in the room today, so if you see them, go ahead and talk to them. So let's just jump right into it. So in 2020, Sarah Hooker from Google Research released a paper titled The Hardware Lottery. And the thesis of this paper, at least in my eyes, is that hardware and compilers have a disproportionate role in deciding which research ideas succeed or fail. And she argues, for example, that the current track of matrix multiplication-based advances in machine learning are inherently linked to the abundance of hardware for matrix multiplication, and that other research directions in the area of machine learning have definitely been impacted by this and are subsequently less likely to be successful. So, in my eyes, the hardware lottery is a direct challenge to all the people in this room. By my reading, specifically, the takeaway for our community, the PL and architecture community, is that any new platforms, any new hardware and their associated compiler stack that is built today should be easier to build so that the best ideas win, not just the ideas that have the hardware associated with them. So, in this talk, I'm going to be focusing on what I specifically know, which is compilers. I don't know all that much about hardware, so let's focus specifically on compilers today. And let's just jump in right away by asking the question, why are compilers so hard to build? So imagine we have a hardware engineer who builds a new hardware design. If she wants to run programs on her hardware, she's going to need a compiler that compiles programs down to her design. This requires a compiler engineer who, with much time and effort, builds a compiler whose design is informed not only by the hardware design itself, but also by communications with the hardware designer, any documentation that exists for the hardware design, and finally, and most confusingly, by the compiler engineer's own internal model of how the hardware works. If that's not confusing enough, if the team wants to ensure that the compiler is correct, they're going to hire a verification engineer who's going to build a formal verification model which models the hardware and verifies that the compiler is correct. Similarly to the compiler, the design of the verification model is informed by communications with the hardware designer, the hardware design itself, the documentation, and also the verification engineer's own ideas about how the hardware works. So if this is looking a little complicated, I completely agree. The process of building a compiler, though, is more than just confusing. It also requires significant developer effort, which you can plainly see once you see the sheer number of individual contributors and the number of years that have gone into major open source compilers like GCC, the hardware synthesis tool Yosis, and the open source deep learning compiler TVM. And furthermore, building a compiler is kind of a notoriously bug-prone process. In fact, you can build a really good research career just on finding bugs in these tools. This is a completely worthy area of research. So, to make matters worse, on top of the time and effort and the bugs, all these costs are multiplicative. That is, every time you want to build a new piece of hardware, you have to repeat these costs. You have to repeat this process. And there definitely, there exist compiler frameworks like LLVM, MLAR, that lessen the burden on compiler engineers, but it still requires a lot of experience to actually use these frameworks. So we asked the question, why are compilers so hard to build? What we've seen is that building a compiler requires significant engineering effort and induces numerous bugs. And furthermore, and kind of most importantly, these costs are multiplied with every new hardware design. So a natural question to ask after all of this is, what if compilers were synthesized? Or what if we could automatically generate compilers? And this might sound optimistic given how complicated it is to build a compiler, as I just showed, but let's dream a little bit. Let's entertain the possibility. So in the ideal case, in this ideal world where compilers were automatically generated, we would still have our hardware designer build the hardware design, but now that design would be read by some kind of compiler generator, which generates a compiler from their hardware implementation. and from any associated information about that hardware. So automating this compiler construction would save an immense amount of engineering effort and time, and in addition, depending on how the compiler generator is built, the generator could automatically verify the compiler as it's being generated, producing a bug-free compiler. But best of all, this approach can scale. So every new hardware design can actually reuse that same compiler generator. And in this ideal world, there really is no hardware lottery. At least there's no hardware lottery because of compilers. So if compilers are generated, automatically generating compilers could reduce engineering effort and eliminate bugs. And furthermore, the approach can scale with new hardware designs. And this fights against the hardware lottery, kind of the core problem underlying this whole talk. So with that, I'm going to go ahead and introduce the thesis of this talk, in which I claim that compilers should be generated from more formal models of hardware. And this itself is not a new idea. I think there's going to be a lot of talks that kind of hit on this idea today. So we're not claiming this as the main idea, but really what we want to talk about is why now specifically is the time to do this. So furthermore, we state that with the growing diversity of hardware and the rapid improvement of automated reasoning, now specifically is the time to make this a reality. So here's the roadmap for the rest of the talk. Let's talk about why now specifically is the time to do this kind of research. We claim that with the growing diversity of hardware and the rapid improvement of automated reasoning, now is the time to make automated generation of compilers a reality. So let's talk about what we mean by the growing diversity of hardware. So as soon as I mention diversity of hardware, I think the first thing that's going to pop into most people's minds is machine learning and hardware for machine learning. So we have GPUs, we have custom machine learning ASICs. But even on processors like Apple's A16, we're seeing the addition of specialized accelerators like GPUs and neural engines. You can also consider platforms further outside the realm of ML. So platforms like Xilinx's Zinc chip, which includes both an ARM CPU and a reconfigurable FPGA, which makes quite an interesting target for compilers. And lastly, far from the realm of ML, from processors, from silicon-based computing as a whole, people have begun computing using things like DNA strand displacement or metamaterials. And these are far from what we would normally consider hardware, but nonetheless, they still require compilers. So given this dizzying array of hardware available today, it's clear that hardware is growing more diverse and more compilers are desperately needed. And this diversity can be really intimidating. How are we going to generate compilers for all of these varied hardware targets? But as the explosion of new hardware, as we see this explosion of new hardware, it actually works in our favor. We don't necessarily need to be intimidated by it, because as hardware diversifies, it actually gets more specialized, and thus potentially easier to target with automated methods. So there's plenty of previous work in the area of automatically generated compilers, and this previous work largely focuses on processors, general-purpose processors, generating compilers for general-purpose processors. And generating compilers for processors is actually a very difficult task, because processors are general-purpose, and compilers for general-purpose processors have to be themselves general-purpose. They have to handle all the possible edge cases and all the things that this compiler or this processor can do. On the other hand, all the new hardware we're talking about today is special-purpose. All the hardware on this slide is special-purpose, which makes the task of reasoning about hardware's behavior much more feasible for automated methods. But not only is our hardware more amenable to automated reasoning, our tools for automated reasoning are now powerful enough to scale to tasks of compiler generation. Consider, for example, SAT and SMT solvers, whose performance has been steadily increasing over time. Or the relatively new technique of equality saturation. Shout out to the eGraphs workshop happening tomorrow. People should go. Which has already shown great promise for compiler construction. And of course, it wouldn't be a talk in 2023 if I didn't mention large language models, which are powerful tools for generating hardware code among many other tasks. Given that this is only a small selection of the automated reasoning tools available today, it's pretty clear that automated reasoning tools are ready for the task of compiler generation. So why is now specifically the time to make automated generation of compilers a reality? Well, first, hardware is diversifying, and we need new compilers. We have to do this. But furthermore, modern targets are more amenable to automated methods. As they become more specialized, they become more amenable to automated reasoning. And finally, automated reasoning tools are now ready for this bold task of compiler generation. Now, let's talk about a very concrete example of generating a compiler from hardware models in a project that we're working on called Lake Road. So we keep talking about this growing diversity of hardware platforms. Now let's take a look at a concrete example of growing diversity, and we're going to look at FPGAs. So FPGAs are reconfigurable devices that can be used to implement hardware. At a high level, though, you can really just think of an FPGA as being a bag filled with parts that we call primitives, or FPGA primitives. In the past, FPGAs consisted only of lookup tables, which are primitives that can be configured or reconfigured to implement logic gates. Over the years, though, FPGAs have added specialized primitives, such as carry chains, to implement fast arithmetic. But one of the most interesting and impactful additions to FPGAs has been the inclusion of digital signal processors, or DSPs, which are small, programmable, embedded processors. So we can see that even within FPGAs, hardware is diversifying. So then we can ask the question, are new primitives a challenge for FPGA compilers, as our thesis might suggest? As FPGAs are becoming more diverse internally, do compilers struggle to target those new primitives that are being added to FPGAs? We can test this with a really simple experiment. We're going to attempt to compile this simple hardware design onto specifically a Xilinx FPGA's DSP. In our case, the simple design takes 4 inputs and it computes this expression over 3 pipeline stages. So the Xilinx DSP documentation claims that this expression is supported on a DSP. But when we attempt to compile our design using the state-of-the-art compiler for Xilinx FPGAs, we see a surprising result. We see that the design is in fact compiled onto, it is compiled onto DSPs, but instead of using a single DSP as expected, it uses 2 DSPs and 10 additional lookup tables. So we asked the primitives a challenge for FPGA compilers. And from our very brief experiment, it seems like the answer is potentially yes. But this should be completely unsurprising to us, because DSPs and other complex primitives are really complicated. I mean, if you just look at the manual for the Xilinx DSP alone, it's over 75 pages long. Furthermore, instantiating a DSP requires setting over 100 parameters while obeying strict requirements on ports and parameter values described throughout a 75-page manual. And with all of these complex interdependencies on what values are legal for which parameters based on the values of other parameters, all specified in this manual, configuring a DSP is starting to sound a lot like writing a program. So that leads us to our first insight of Lake Road. Our first insight is that configuring DSPs and other complex primitives is similar to writing a program, so why not just use program synthesis? For those unfamiliar with program synthesis, I'm not going to go into too much detail, but just know that solver-aided program synthesis is the process of using SAT, SMT, solvers, etc. to generate programs by solving a set of constraints. And because configuring DSPs is so complicated, Xilinx actually provides a 1,500-line simulation model of the DSP and all of its other primitives, which hardware designers can use to validate their designs. But this tool is actually useful to us as well, not just for simulation, because simulation models provide the formal semantics of behaviors and constraints necessary for automated reasoning. So that leads us to our second insight, which is that we can actually extract the semantics necessary for automated reasoning, i.e. reasoning with a SAT solver, reasoning with program synthesis, directly from simulation models. So we use these 2 insights to build Lake Road, which is a hardware synthesis tool utilizing program synthesis and semantics extracted from simulation models to target complex programmable FPGA primitives. I'm not going to talk about the internal details. I'm happy to talk about them afterwards. We're currently writing a paper on this. But initial results with Lake Road suggest that Lake Road is able to find mappings that other tools do not, successfully mapping designs onto a single DSP when other tools fail to do so. So how does Lake Road support the thesis of this talk? We claim that compilers should be generated from formal models of hardware, and Lake Road does this by automatically enabling compilation to FPGA primitives given just the simulation models of those primitives. Furthermore, we claim that with the growing diversity of hardware and the rapid improvement of automated reasoning, now is the time to make this a reality, and which Lake Road demonstrates by showing that automated methods are now powerful enough to address gaps in state-of-the-art tools. So let's finally conclude with a call to action. So in conclusion, I want to end where I began. I believe the hardware lottery is a direct challenge to every single person in this room. If there's one message I want to leave you with today, it's this. It's on all of us in this room to fight against the hardware lottery by making sure that practitioners in all fields have the hardware and compilers they need to advance their specific research. What I've proposed today, which is automatically generating compilers from formal models, is just one possible solution to this. Whether or not you agree with that solution, I hope you're going to agree with the larger goal of ending the hardware lottery once and for all. Thanks, everybody.
So we're going to have one other talk in this block now, and then we'll do a discussion and Q&A session. Could we have the speaker for the Senate on America?